So if that's your plan, also don't go to school. Like seriously, go get a job in HVAC apprenticeship. Get an apprenticeship and work there. You'll make more money, learn better, and have all the things. Yeah, it's a waste of time and money to even that is the biggest. These quote unquote trade schools are honestly the biggest scam of it all. I don't agree with the blanket sentence. College is a scam. I think that's a misleading sentence. I understand why Charlie would say it. I get it because he's trying to wake people up and make them think, and I get it. It's great. It's fine. No problem with that. But honestly, trade schools, a lot of them are a scam. Just go do the job with people who are good at the job.
Take Sean to electrical
class out of it that actually means something is not really.
Yeah.
Sean's electrical class. That's
No, that won't help you become an electrician. That won't help you become an electrician at all. Not even slightly. That's not what that class is about. Designing, not really designing computers, but it would be more like if you want to. I mean, it's kind of a basis for a lot of stuff, but like, if my class is preparing you for something specific, it'd be more like robotics. Like it'd be preparing you to become an engineering tech at Boston Dynamics. I mean, which is definitely a up and coming field for sure. So, all right, we got some trigonometry to do. I turned way too far. We're not talking about parabolas yet. All right. I gave you 2 through 42 or 44? 42. Number 2. Sine is 2 times the square root of 14 over 15. Cosine is 13 over 15. Tangent is 2 times the square root of 14 over 13. Cosecant is 15 times the square root of 14 over 28. Secant is 15 over 13. Cotangent is 13 times the square root of 14 over 28. Number 4. Sine is 12 37ths. Cosine is 35 37ths. Tangent is 12 35ths. Cosecant is 37 12ths. Secant is 37 35ths. Cotangent is 35 12ths. 6. Sine is 6 sevenths. Cosine is square root of 13 sevenths. Tangent is 6 times the square root of 13 over 13. Cosecant is 7 over 6. Secant is 7 times the square root of 13 over 13. Cotangent is square root of 13 over 6. 8. Square root of 17 over 17. Cosine is 4 times the square root of 17 over 17. Tangent is 1/4. Cosecant is square root of 17. Secant is square root of 17 over 4. Cotangent is 4. 10. Sine is the square root of 13 over 7. Tangent is square root of 13 over 6. Cosecant is 7 times the square root of 13 over 13. Secant is 7 over 6. Cotangent is 6 times the square root of 13 over 13. 12. Sine is 8 times the square root of 7 over 8. Cosine is 1 over 8. Tangent is 3 times the square root of 7. Cosecant is 8 times the square root of 7 over 21. Cotangent is square root of 7 over 21. 14 is square root of 7 over 17. Cosine is 4 times the square root of 7 over 17. Square root of 17 over 17. Cosecant is square root of 17. Secant is square root of 17 over 4. Cotangent is 4. 16 is sine is 1 over 6. Cosine is square root of 35 over 6. Tangent is square root of 35 over 35. Secant is square root of 6 times the square root of 35 over 35. Cotangent is the square root of 35. 18, square root of 105 over 13. That's cosine. Tangent is 8 times the square root of 105 over 105. Cosecant is 13 over 8. Secant is 13 times the square root of 105 over 105. Cotangent is square root of 105 over 8. 20 is 6.5. 22 is 17.5. You're saying yes, like, hey, I can put something in the calculator. Good job.
Oh, wait, I forgot what those were.
24 is 22.2. 26 is 71.2. 28 is C margin. 28A is a triangle with an 18-degree angle and 3.5 feet on the altitude. 28B is 11.3 feet. 30 is 190 feet. 32 is 48 degrees. 34 is 81 degrees. 36 is 46 degrees. 38 is 69 degrees. All the ones that have degrees, the answer, if you didn't put degrees, it is definitely wrong because 69 degrees is way different than 69 radians. Continuing on. Number 40 is 84 meters. 42A is a triangle with 55 degrees down at the bottom and 375 feet as the hypotenuse. 40, oh no, that's just kidding. That's 41A. How about 42A? It's got 48 degrees and it has altitude of 225 meters. 42B is 303 meters. 44A is a little skinny triangle with another little triangle inside of it and all the things labeled out. But it'll be easier to know whether you got it right if I just say that 44B is 2,310 meters. And if you got that right, you probably drew the picture right. What? We didn't do 44. Oh, why not? It's a great problem. Oh well.
Could you repeat 32?
32.
No. The answer to the problem, 32.
48 degrees.
Okay, good. I'm fine with that. Yay.
What questions do we have on this lesson?
28.
Yeah, I want to do 6. I don't know what happened. But
Y'all
6.
Y'all forgot to divide by 5 out of that.
Yeah, you probably just need to reduce.
Oh, yeah, that's definitely what happened.
Is that what you have? Is that what happened on yours, Malcolm?
What I see.
What?
I'm not. That's
Yeah, I
not
can
right.
reduce everything very easily.
On 6?
7, on 6, or 13 over
What are your answers?
7. We got 6 7s. 6 7.
Square root of 13 over 7. 6 times square root of 13 over 13.
Yeah, those are all right. What is? Did you ask for it, or was it Landon that asked for that one?
Looking at the wrong question. Malcolm asked.
Malcolm asked for it.
Yeah, those are all right, sir.
7 times square root of 13 over 13.
Yeah, those are all right.
Can we do 28?
Mm-hmm. Snowboarding.
Never mind.
I messed something up on one of the questions. I don't know. I messed something up on one of the questions. Probably just wasn't 6. 8. Oh, 28 is pretty easy. It's just Pythagorean.
8.
Inverse thing.
You're asking for 8?
28.
Yes.
Oh, he's asking for 8.
What did you get for 8?
Uh,
That one also reduces.
Square root of 17. 4 times square root of 17.
Square root of 17 for which one?
Huh?
Square root of 17 for which, like,
For
sine, cosine?
cosine. 4 times square root of 17 over 17 is cosine. Sine is square root of 17.
Sine is square root of 17 over 17.
Sine square root of 17 over 17.
At least that's what it says. Let's see. Let me look at it. It should be 8 over the square root of 17, right?
did you do the Pythagorean theorem right?
Maybe I did that wrong. It's
Oh, it's not. What is when you do the Pythagorean theorem? It's not square root of 17. It's Pythagorean.
8 times
It
the square root
It's
of
8 times.
8.
the
Yeah. So
And it's 8 over.
it'd be 1 over the square root of 17. You'd look at it backwards.
Okay.
So square root of 17 over 17. You just looked at it backwards.
I like this unit so far, Sean.
Well, good.
Makes sense.
See if we can ruin that for you.
Can we do it over 28?
You know, if you do electrical engineering, just saying,
Yeah.
this particular unit is important for you.
I don't understand.
Not this lesson necessarily, but this unit is important for you. Anyway, what number did we say?
28.
You are you actually asking 28 this time?
Actually,
Oh my gosh. Okay.
28, okay, I can-
Brad built a snowboarding ramp
oh my.
at a height of 3.5 feet and an 18-degree incline. Okay.
I
Draw
dropped
the
them.
thing on the left side is 3.5 and then 18 is the thingy, the degree.
Yes. Yeah, and that's what I did. And then 18 is that angle.
Great. And then
You put it
so
in
that's part A done. Length of the ramp. What trig function
No, we're finding the length.
of the ramp?
Yeah.
That's
This
what
is
I
the
did.
ramp.
I found the length of the bottom.
Yeah, yeah.
Never mind.
I figured that's where we were going with the mistake, but yeah.
So OH,
Yeah.
so sine, it's not negative sine.
No, it's not inverse sine. We have the angle. It's just sine.
Oh,
Sine
yeah.
of 18 equals that. And then we do
Yeah.
3.5.
What other questions from this lesson?
That.
I don't know.
And it gives us
That's not what I would put in my calculator. I would put Yeah, it's just more efficient.
I just find it easier to do it with that.
All right, let's do
Alright.
4-2. Degrees and radians.
Oh, keep going.
Degrees and radians. You're not him.
You're not that guy, pal. You're not that guy. We are learning a new unit.
A new unit.
Yes.
Oh no. Oh no.
It is a wonderful unit.
We love radians.
We do. And I am telling you that, and I am including you in it because I want you to love radians.
I love
Don't learn, if you can get to the point when you're learning a foreign language like Spanish or something, if you can get to the point where you're thinking in that other language, you're doing good. If you will push to do that with radians, several of these problems are like so much easier if you just stay in radians. Because all you have to look at is the denominator. It's great. It might mean you have to deal with fractions a wee bit, but check your worries at the door and you got this.
Worrying about fractions is so middle school.
So middle school. So middle school.
Yeah,
Okay.
whatever you have.
This is an axis, right? Right. Right here at the positive x-axis is 0 degrees. Isn't it cute? That's not 0 to the 0, that's 0 degrees.
What is 0 to the 0?
0 to the 0 would, 0 to the 0 is actually kind of a paradox, which is whatever else, and it's discussing 0 to the 0 is beyond the scope of today's class. It is there's some quite fun discussions that can be had, but it's beyond today's scope.
That sounds like
During midterm review.
All right. When we are naming angles on axes like this, this is the beginning. This is the termination, the terminus. And we go, and positive angles go counterclockwise, this way. So this would be 90 degrees. True enough, right?
This makes sense.
This does. This would be 180 degrees. 270 degrees.
And then 0 degrees is also 360.
And it's also 360. And if we keep going, we keep adding, right? You can keep spinning around and around and around.
Double backflip is 720.
Yeah. A double, I don't know why it's specifically a backflip, but going around twice is 720. Yes. Okay. Whatever helps you remember things. Right? We also have some other important angles that we should label on our thing. Don't forget, we're taking notes. And we've already demonstrated
He can erase things.
that I can erase things.
I'm noting down.
I am glad you are mentally participating, and I want you to continue to do that. That is good. Okay, so there's some other important angles on here that we need to think about. One of them would be 45 degrees, right? We do lots of trig with 45 degrees. It's one of our quote-unquote special angles.
How did I know we both were going to say that?
Because he is special.
45 degrees is a special angle. There's a couple other special angles. What are they? 30 and 60. That's true. They are also special. That's more like 15, but whatever. 30 degrees is also special. And 60 degrees is also special. And if they're special, their counterparts here, here, and here are also special. That's true.
Yes, that makes sense.
There's a one right in the middle. What's the one right in the middle that would correspond with 45 degrees? 135 degrees is also special.
And so is 120.
120 degrees is also special. and 150 degrees. Although, which one do those correspond to?
150 to,
Oh.
I think 150 to 60. No,
Agreed.
20 to 30.
150 corresponds with 30.
Ah.
120 corresponds with 60. We'll talk about that when we talk about standard position angles and all about that stuff, but getting that in your brain now. Now this is much easier in radians. You're going to see why when we have the unit circle in radians.
Okay.
Because in this you have to like sit there and do math for half a second to think, okay, what is this thing? In radians you just look at the denominator. What would be the one that corresponds with 45 degrees over here in quadrant number 3?
It would be 225.
It would be 225.
Degrees.
And which one would correspond to the 30 degrees over here?
210.
210. And what would correspond to the 60 degrees over here?
240.
Have y'all heard that people are trying to push for the great meme reset of 2026? People are pushing for, like, they're tired of all of the new brain rot coming out every other day, and like, okay, we're going to start going back to like earlier 2020s and just using old stuff again.
You'll just die.
Just do things like instead of 6, we go back to 21. Anyway, what would be the 45 degrees over here?
315.
It would be 315.
And then we have 300 as 60.
Yep, that one's easy to math, right? You can hack it.
300.
Yeah, I don't know why I wrote 360. That don't make no sense.
365 no scoop, my dudes. 365 for Whole Foods.
Not the degrees
Okay.
of the circle.
365 by Whole Foods.
So those are important when we're talking about this, right? So if you want to find oh, I'm sorry. I was looking at the book and I was confused about what it was saying. I need to quit doing that and just keep teaching. Anyway, continuing what's happening, yes, the book is right that a degree is 1/360th of a circle. I don't know why it was telling me that, but it was. But that's what a degree is. Actually, I do know why it's telling me that. So we're not quite there yet. We got to do one other bit, and the only reason this is in here is honestly I don't even remember whether I put this on the test or not. This is like almost a trivia thing, like thrown in this lesson. And it's not unique to this book. It is using a slightly different degree measure. Because we can have fractional degrees, decimal degrees, right? You can have 30.87 degrees. That's true. If we're a captain of a ship, we might write 30.87 degrees differently. We might use minutes and seconds notation. So we're going to do an example like guided practice 1A.
On which page?
2, no, what are you saying? 232.
I'm going crazy, Sean. No, I'm trying to miss again.
Okay, so we're going to convert 213 0.875 degrees to degrees, minutes, seconds, which is a way of turning that decimal into something else. And it's really easy because the name tells you how to do it. Okay? You're converting that to minutes. How many minutes are in an hour? 60. So how many minutes are in a degree? 60. True enough. Goofy goober.
What? 60 minutes in a degree.
There are 60 minutes in a degree. So, this is 213 degrees plus 87.5.
Okay, times 6. 60.
Actually, that's not quite right. I didn't quite. I've missed something, right?
Yeah.
Because it's 0 point that, right?
Oh.
Times 60 over Juan. Yeah. What do we get?
Juan Soto?
0.875 times 60 equals 52.5.
52. So it is 213 degrees, 52.5 minutes. But that's still ugly. We want to get the decimal away. We want to go
Why is
0.5. It is because of it's easier to describe when you're trying to say you need to go turn the wheel to that. I think. I don't know. I actually have no idea why this exists, but it's a thing.
So we have to learn it. This
Times 60 again. So this number in degree, minute, seconds notation would be 213 degrees, 52 minutes, 30 seconds. So to go the other way around, you just divide, right? The only tricky bit is when you're going from the seconds part, you got to divide by 3600, not by 60.
So we don't divide by 60 and then put a decimal place and combine those two and divide by 60.
You probably could do it that way. You'd have to double check to see whether that method also worked. But if you kind of want to do it in one shot, you do it that way. I'll leave the example in the book to be the rest of that. Okay. So radians is what we're talking about new today. So there's that. Yay, radians.
He's trying to stab me with a pencil.
What is the, I can't think how to phrase what I'm asking and to make it useful. Circumference of a circle and the radius of the circle are kind of like the whole definition of a circle, right?
Yeah.
Like that's how they work, right? So when we're doing a circle, I was right. I was gonna go get a bowl, but then I remembered I had a bowl. Didn't put a bowl back from last year. I do got a bowl.
I think he's gonna draw a circle with the bowl.
I think he's going to draw on.
Of course he's gonna draw on the 420. What else would he draw on?
All right. Isn't he cute?
Use the ball for a circle. What else would he use for a circle?
I don't know.
So what we're setting up for in learning radians, and because we have the ability to not be a book, I can kind of like talk about more than one thing at once, right? So we're setting up for lesson 3, which is talking about unit circle, trigonometry, which is a different way to think about trigonometry than just with triangles. Okay? It is, and that's where we're going. And we're going to where we can think about trigonometry. If we make the r just 1, then it just works. Because no matter how long this is, that angle is still the same, right? Yeah. Right? Which is useful. Okay, so we've got this, and we're gonna force a bit of a triangle onto here.
Oh.
What?
I see it. I don't.
I do.
I don't know if you do. I don't understand what you're talking about, bro.
Are we going to draw another line?
I see a triangle. It's exciting.
It's not a triangle though.
No, it's not a triangle. That's why I said a sort of a triangle.
Oh.
This guy is an angle. Whoa. Astonishing. Now that angle cuts something. What is this called?
Circle.
Yeah, the whole thing. What is this called?
Arc.
It's called an arc. It cuts an arc length.
I thought you said arc length.
Arc length.
Does it use S? Yeah, it does use S. That's what I thought we were doing.
Baby arc, it's an arc length.
That's what I just said.
I can't hear you.
Radians is useful because it's a ratio.
What is the ratio?
It's a ratio. It's a ratio of a circle's intercepted arc length to the radius. So a radian.
It's the degree over the radius?
It's the S.
Or is it the radius over the degree?
It's the S over R. But I don't know why.
Oh, it's the delta.
It's the S.
Theta.
It is the S over R. That's true.
S over R equals delta?
Oh shoot, I need to draw this.
That's not a delta, bruh.
Whatever the heck that thing is.
That is a theta.
You said delta. I said theta.
Did I say delta?
Yeah, you did say delta.
No, you definitely did. You definitely said theta.
So theta in this definition is the angle in radians.
So theta equals S over R, question mark?
So the angle is.
Yeah, that's literally what's on the board. Where's the question mark?
Okay, your body was in front of the
Oh,
thing.
well, yeah, but it wasn't when I wrote that.
I wasn't paying attention when you wrote that.
That's crazy. So not only were you not copying down notes, you weren't even paying attention.
copying down notes.
That's
That's why I
cringe, bruh. That's cringe. Cringe.
That's what happens after
That's
20, 26 resets. You start saying
crazy.
cringe again.
Let's build this in radians. Radians they don't have to be, but when we're doing math with radians, they are very often left in terms of pi. You're going to see a lot of pi.
Wait a minute.
I like pies.
If we make R 1 always. Pi is a fun number. And also it takes way hard every time.
We'll get to that in lesson 3. Lesson 3.
You just divide by the thingy and then.
Let's build this. I don't know. Well, where's my bowl? Give me my bowl back. I want my. Well, no, it doesn't work. Doesn't work. Doesn't work at all. It's valiant effort.
This guy next to me is screwing things going. Bowls and planes and bowls.
This guy next to me has 3 inches tall hair.
Yeah. And you have like a hat. And you have like a hat.
Whoa.
Okay.
These guys next to me have.
How many radians is it right here?
0.
0. That's true enough. That's true enough. 0 radians. How many pi radians is it going to be right here?
I have no
0.
Or
1.
2.
Isn't it 1?
It is 1 pi radians right there,
What? 0.
which is the
I've seen
same
this
as
before.
180 degrees.
I've played these games before.
You have seen it in geometry.
I don't remember this.
Wait, does that mean that
I've seen it in
the one in the middle
videos.
is like the
That may be true.
like half pi? What's the half pi again?
So what would 90 degrees be?
It's the half pi, whatever.
Pi over 2.
No, there's 2
Wait, so
pi.
it is the half pi.
No, it's 2 pi. There is not a thing for half pi. It
Yes,
is
that's
2
where
pi.
there's for 2 pi.
What are you saying? What is anybody
He's saying
saying?
there's another
I feel
variable
like there's
for
like a
half
half
pi,
pi.
but there's a variable for 2 pi.
Yeah, there is. Tau.
Tau. I don't know how to draw it though. It's
Wait,
like-
so 0 is also tau.
Ah.
Does that mean 0 is tau
No.
as well?
No.
No, that's
0
that's
is
not
0.
what I'm.
0 is 0.
Anyway, how many pi radians would this be?
1 pi. 1.1 pi.
1,
3 pi over 2.
3 pi.
3 pi over 2.
1.5 pi.
Oh. Wait a minute. I
And
think
then
I get it.
the other, this is.
How many pi radians would this be?
Theta.
2 pi.
The thingy. What I just said.
Oh my cow.
See, what? Oh, we can't use tau.
Landon is trying so hard to sound smart,
I am.
and it, as a result, sounding failing. No, you're not stupid. It's just you're trying so hard to sound smart that it's like not working at
I'm
all.
quite stupid in like saying the.
Half pi. I mean 2 pi. What is it called? Theta.
All right. So what about
I'm gonna smack you.
It's okay.
It's okay. Don't.
halfway between there?
1/4 pi.
Pi over 4.
Pi over 4.
I think this pi button on my calculator is going to get very tired.
You're not going to push the pi button. You're going to leave it in terms of pi.
Where's the pi button even?
You're not going to push the pi button at all.
Good.
You're just going to write pi.
Holy crap! I do love rating.
Oh, I found the pi button.
Nice, great. How many pi radians is right here?
1/4.
It's 3/4 of the, or excuse me, it's 1/4 more than pi.
Pi over 4.
5 pi over 4.
Oh, that makes sense. Okay.
Doesn't.
It does make sense.
And then this is 3 pi.
It's almost like the math is mathing. What would this be?
3 pi over 4.
Yeah, 3 pi over 4. What about this one?
7 pi over 4.
7 pi over 4. What is this one?
Oh, it's
Pi over 8.
No.
Oh, the
Pi over 6.
pi over 3. No.
Pi over 5.
Oh, that one? Oh, shoot. That's not
Pi over 16.
Wait.
Pi
No,
over
it's
eight.
not. It's gonna be. It's 30 degrees. 0 degrees is 2. Is 0.
It's in between pi over 4 and 0.
Pi over 3.
6. He already said 6.
It's a sixth of the, yeah, y'all were just saying random numbers. I stopped listening a long time ago.
6 was the first one I said,
First one he said.
and then I said 8, and then I said 16.
And then you said 6 again.
I said it wasn't 8, and then you never circled back to 6, so. What would this one be?
Pi over,
Pi over 3.
yeah, because it'd be 2 pi over 6, so just pi over 3.
1/3 pi. Wait, no.
Pi
Pi over
1/3.
3. Never mind.
Pi, 1/3 pi is pi over 3.
Okay.
Same. What would this one be?
1/2.
2 pi.
Wait, no, never mind.
2 pi over 3.
Definitely not.
4.
Pi over 6.
Or is it 2 pi over 3?
No,
2 pi over 3 is the same thing.
That's 6 pi over 8.
What? Where'd you get over 8? It has to be
6 pi over 8 would be 3 pi over 4.
2 pi over 3.
Yeah.
2 pi over 3.
3 pi over 4.
2 pi over
Wait,
3.
is it 2 pi? Wait. 2.
Is it 2 pack?
Shut up.
It can't be 1/2 pi because we already have 1/2
Is
pi.
it something over 6?
2 pi or
2 pi over 3?
How is
2
it-
pi over 3.
You kept saying that.
That's what I said.
Why
I literally
so
said
long?
this.
You didn't say that. Quit
I
lying.
said
I
that.
said that like 8
I
times.
said-
Yeah, he
I said
did.
it 8 times.
You didn't say it once.
I
No,
said it.
we
many
didn't say it
times.
once.
I said 2
No.
pi over 3. 2 pi over 3. 2 pi over 3.
Now you're saying no.
2 pi over
It doesn't
3.
make up.
What's the next one?
5 pi over 6.
Yeah, 5 pi over 6.
What would this one be?
7 pi over 6.
What about this one?
4 pi over 3.
What would this one be?
10 pi over 6, or 5 pi over 3.
That's not how that works. You just divide one thing by 3 and then 3 by 3.
So
7
10
pi
pi over 6, or 5 pi over 3.
why you're doing it that way. Just do
What I'm doing
2 with a 3 in the denominator, so 6 pi over 3 minus
I've just been adding
1 pi over.
as we go and then having to divide by 2.
You're doing a lot. You're doing a lot, bro. What is this? What is this one? What are we writing? 5 pi over 3. 6 pi over 3. 6 pi over 3 minus pi over 3. 6 minus 1 is 5.
Say that again?
All the way around is 2 pi.
Yes.
You're subtracting off pi over 6. I mean pi over 3.
Okay.
So 6 pi over 3 minus 1 pi over 3 is 5 pi over 3. What's this one going to be?
11 pi over 6. No? Yeah, 11 pi over 6.
True enough.
So every 6
My
is
circle
a
was too
30-degree
small.
angle, every 3 is a 60-degree angle, and every
When we're talking about coterminal ones, yeah. Yes. Okay.
What is it? Every time there's a 3 in the denominator, it's a 30-degree angle. Every time there's a 4 in the denominator, it's a 45-degree angle. Every time there's a 3 in the denominator, it's a 60-degree angle.
I just got cut up because I can't read it.
Okay. If you wanted to just straight up convert things to radians, the way, so you're either going to multiply by pi over 180 or 180 over pi, and we would convert between degrees and radians. And I find it much easier to think about whether I want a pi in my answer or not. If I am trying to convert 2 radians, I want a pi in my answer, so the pi goes in the top. If I'm trying to go from radians 2 degrees, I don't want a pi in my answer, so the pi is going to go on the bottom. And that's how I think about it. So like if we're going to convert 12.86 degrees to radians, we do 12.86 times pi over 180. And we want pi to stay, so we just do 12.86 divided by 180, preferably as a fraction for our answer.
Dang. Why do I automatically make this term fraction?
I forgot what that pi went.
You don't need pi.
Pi is staying in.
No, I'm saying I have to multiply 12.86 times.
No,
Look, actually listen this time, because clearly you were, let's put your calculator down. Like, actually listen this time. In radians, we want pi to sit there.
Yeah.
So it's x, it's a variable. It's not, you're never gonna do times pi, because it's either gonna cancel or it's gonna stay there. So just do this divided by this and then give me a fraction.
Why won't I let it be a fraction? Keeps giving
I
me
know how to make the, you gotta use the
0.714.
fraction bar.
I did, but it gave me 0.0714 repeated. And that's not a fraction. I don't
You
know how to
convert
choose.
that to a fraction by.
Landon, you just got a fraction. It's that SR or whatever, SD or whatever it is.
It's 643 over 9,000.
Yeah.
Did you find it?
Yeah, I had to hit the math.
Yours is wherever it is here, this guy.
Oh.
And it just converts back and forth.
That's useful.
Yeah. All right, so what is the number?
643 over 9,000.
You took the easier step. I took the harder. 643, not 6.
Okay. So if I want to convert
It don't matter that much.
8 pi over 17 to decimal, I multiply it times 180 over pi.
I's cancel. And then
Yeah.
8 times 180 divided by 7.
Yeah. Which is going to be something ugly. What is that ugly something?
It's 84.71 degrees. Unless you want it as a fraction.
You could do it as a fraction. It'd be whatever 8 times 180 is over 17.
It is 100.
140
over 17.
Sounds right. Sounds correct. I think we're done with this lesson. No, I'm not wrong. Good. Good. We've got, let's see, what else? We got coterminal. Oh, yeah, there's a lot more in this lesson. Time we got. I bet we got enough time to squeeze it in. Let's do it. All right. So I have been alluding to something, and I've been saying words excuse me. I've been saying words that are true, but I haven't told you what they mean or given you definitions for them. I'm alluding to one of the reasons why radians are really handy. Okay, so the first thing, I'm going to go a little bit different order than this is. Where did my marker go? I had it 2 seconds ago. Oh, there it is. What's the matter?
That one fraction that we just did wasn't converting on me for some reason.
Well, you wouldn't have to convert it because it doesn't pre-reduce, so it's not going to post-reduce, so just multiply the tops together and put it over 17.
Yeah, it literally didn't work.
What is the GRA mode? There's degree radians.
Gradients.
Gradients?
Yeah.
Is that a half radian?
I actually have no idea what gradients is. It's some specific engineering unit for something. I have no idea, to be honest. To be 100% honest. Couldn't tell you. I've never cared. Never learned it. Okay. So, I'm going to give you a couple things, one of which is not really in this lesson. It's really coming later, but I'm giving it to you for some intuition now and some work later. So, that is an acronym. The acronym is All Students Take Calculus. That's the acronym. And it tells you this. All students take calculus. Starting in quadrant 1, we go around. And what this is telling you, and this is more for later, but it relates to what we're learning now or what we're about to learn. And so kind of keeping that intuition all put together. It's telling you which trig function is positive in which quadrant. In quadrant 1, they're all positive. In quadrant 2, sine is positive. In quadrant 3, tangent is positive. In quadrant 4, cosine is positive.
So with secant, cosecant, cotangent.
They follow their reciprocals.
All right, so it would be.
So it'd be like cosecant, cotangent, and secant. Yeah. Yep. Okay, that's really for later. So what we're going to learn about is coterminal angles. Okay. There are two things to talk about with coterminal angles. One is just angles that end in the same place. And that could be angles that like if we have 45 degrees or pi over 4 radians, right? Then it has coterminal angles here for every time it spins around. To get it in radians, we just add 2 pi to that, right? So we just add 8 pi over 4 to pi over 4, and we'd have 9 pi over 4, and it's spun around twice. And then we want to get it, if we want to get it again, if we want to hit that same angle again, we just keep on spinning around. Now, so notationally, if we want to describe all of the angles that smack right there, then we do it with kind of series notation. So if I wanted to list all of the coterminal angles with pi over 4 radians, I would list it like this. I would write pi over 4 plus 2 pi n. And I would circle it and move on with my life. Because that's a representation of all of them. Make sense? Easy peasy. If I wanted to represent all of the coterminal angles with negative 30 degrees. That's a little bit more tricksy. Where is negative 30 degrees?
It's 330.
Yeah, it's down over here. We want to list this positive. So this is actually 330 degrees. So all of the coterminal angles with this are 330 degrees plus what?
330 degrees in.
Not 330.
90. 360 degrees.
360 degrees in. Easy peasy? Lemon squeezy? Great. What if we want to find an arc length? We've got a formula for that. Are y'all in physics? Did y'all take physics?
No, I'm in physics.
You're in physics? When you get to angular momentum and all that stuff, you'll use this formula.
Better write this down now.
And remember it. Remember it good, Malcolm.
I'm gonna write it down anyways when I get to physics, so I'm gonna write it down now. I'm in this.
If you want to find how long an arc is,
Do some math.
you do some math. Easy peasy. You need the angle in radians, and you need the radius.
Couldn't you just always do one?
No.
It wouldn't be to the same factor.
Yeah, it wouldn't be the same. It wouldn't be the same length.
Yeah.
It'd have the same angle, and all the trig functions are going to work the same way because of angles are angles. In order to find the arc length, it's related this way. The arc length S equals the angle in radians, must be in radians for this formula to work. And you multiply it times the radius. Easy peasy. So if we look at problem 4b, example 4b on page 235, and it says to find the length of the intercepted arc with the given central angle measure and radius, round to the nearest tenth if necessary. Okay, so it gives us 135 degrees, and it gives us a radius of a half a foot. So what do we have to do with that one first?
Gotta convert 135 degrees to radians.
Have to convert 135 degrees to radians. This one, if you start to kind of memorize that chart a little bit, you probably just pop out without even doing anything. But what is 135
135
degrees? That's true, but that totally reduces, bro.
Well, but I would just multiply it times.
I would not. What does that reduce to?
Fine.
3/4.
3 pi over 4.
You just use calculator. You cheated.
That was not cheating. I didn't say you couldn't use your calculator. I didn't say that.
Useful.
Okay, so now we're going to shove this in the formula. So to find the length of the intercepted arc, we would do this times a half. And we would get 3 pi over 8 feet. And it says around the nearest, whatever the heck it said around to, tenth. So this is approximately equal to what? Now you do shove your stupid pi button in there. Now we do, because it says to round it.
1.17. I know 1.18.
To the nearest tenth, so it weigh 1.2 feet. Isn't it cute? Okay. Now, let's do another physics formula. How fast how fast the outside of a wheel is moving. So you have learned before about linear speed, right? How fast you move in a straight line, right? You might have even learned how to figure out how fast it's moving in an arc, right? All right, you do two-dimensional motion, all that kind of stuff, right? Easy peasy, lemon squeezy, right? You may, if you're in physics, you probably even use a few trig things in there, but in there it's just like, this is the button on your calculator. Yay, use the formula, great. Right, so we get a little bit more than that. So there is not just linear speed. If we have a wheel, let's get our circular device back again.
Oh, no. Wrong. We need a smaller circular device so we get
If we've got a circle moving, he has two different speeds. He has a linear speed, how fast he's moving this way, and then he's got angular speed, how fast the wheel is turning, right?
Oh, I would think that would be the same because every time it turns, it moves.
Well, one rotation would determine its distance.
Yeah.
One is in degrees or radians per whatever.
Just different.
One is in feet or whatever else, right?
Okay.
Okay, so if S is the arc length, how much it moves, keeping in mind that it could be more than 2 pi, right? More than 360 degrees, because if that wheel goes, it could be more, right? Right, so the arc length in this case could be longer, right? And we want to find out how fast the linear speed is. We use the variable v, and if you're in physics, you probably would write it with a little vector symbol.
Vector.
Oh, yeah.
I know, she doesn't do it that way. But if you were in AP physics, you would. Because that's how the AP physics does. But it is a vector, right? If you're doing linear, if you want to calculate linear speed, you use this formula. You do the arc length that it traveled divided by time, which makes sense. S, what units could we measure S with?
No.
We could. What else could we measure S with?
Degrees.
What else could we measure S with? Inches, feet, right?
Yards.
It's all of our distance. So arcs are an interesting kind of midway bit, right? They're a bit like confuzzled, right? Because they can be linear when you stretch them out, but they also intercept an arc, and the arc length is the same degree measure as the angle, right? So this is the formula. This formula makes sense. If you've learned one-dimensional motion, this makes sense. This is just that formula, right? But if we want to find angular speed, okay, good. For a second, I thought they called it something weird, but they didn't. If you want to find angular speed, velocity is a better word, but we'll use angular speed. That's fine. What's the difference between speed and velocity? What?
No, he said velocity.
So velocity is a vector, and speed is a scalar, right? True enough. What time is it? Is it 12:30?
12:20.
It's almost 12:30. What do we have left? Okay, let me give you these last two formulas, give you some homework and kick you out.
Okay, good.
You find angular speed, you use a Greek letter, This is angular speed. This is linear speed. And you do the angle in radians over time, which makes sense. How many radians per unit of time is the angular speed? This makes sense. Plug and chug in the formula. If you have an area of a sector, so if you have a sector of a circle and you want to figure out how big it is, it's a fraction of the whole. So this formula is going to make sense. How do you... This formula is going to make sense. I'll write it down. You can decide whether you think it makes sense or not. Area of a sector is 1/2 radius squared times the degree measure.
So it's in degrees.
No, in measures. I said the degree measure, but I didn't mean that. It's in radians. Pretty much from here on out, if you see theta, it's in radians. That's not necessarily true, but pretty much. Those are the formulas you need to do some of these word problems. All right, you need to do pages 238 to 239.
I'm guessing 2 through 48.
2 through 62 evens. Goodbye, boys.
We're not boys, we're men.
Sometimes.
That's debatable.
You're getting there.
Even I'm not sure if that's true. Actually, I'm very sure.
You're the reason that's not true.
It's also not for me.
I'm kidding.
It's a triple threat.
It's a triple crown.
None of you are really technically yet in charge and responsible for anyone more than yourself.
Wait, how old are you, Malcolm?
37.
Are you 18 yet?
No.
Gosh dang it, you're not legally yet.
That is the mark of an adult.
I'm legally.
Doesn't necessarily mean you have a family. That's not the only way to be That's not the only way to be responsible for more people than yourself. But that is what makes someone an adult.
Legally.
No, not legally. I don't care about that. Who cares about that? That's just about taxes and money and crap.